Hello, welcome to Matrix Live. Now, where you are sat at this very moment, you are probably sat in the December. You are probably there. This is recorded in December, but it is not the Christmas edition. This is the November edition. So we do not have tinsel. We do not have amazing Christmas jumpers, but we do have some excellent demos for you. And the first one is Jorge, who is going to talk us all through Element X performance.
Yes, hello. Let me see if I can share my screen with the presentation. Can you see it?
Yes.
Okay, so I'll be presenting Element X performance and metrics, or as I like to call it, why is this thing 10 times slower on Android? Okay, so first part is, where do we start from? The Element X apps use the RAS SDK under the hood for most of the logic. And the apps are written in Kotlin and for Android and for iOS, so they're different languages. And to have the SDK and the apps talking to each other, we need to use something called bindings. And through this kind of bridging, through the bindings, we had some kind of bridging, and the bindings are done using Unify. It's a project from Mozilla. And it's basically what we use everywhere, and even in some other parts of the RAS SDK to other platforms. So basically, the bindings for Android have always been a lot slower than they were for iOS for technical reasons. Basically, they need to cross the virtual machine boundary, copy data, and it's overall slower. But recently, Unify got a new version with some important performance improvements. If you see the screenshot, basically, it seemed like the bridging code was now 60 times faster than before. It was huge. And we thought, yay, we're finally catching up to iOS, and we won't have to care so much about how we use the SDK, and we can stay performant. Or that's what we thought. So the cruel reality is actually that, well, the bridging code was actually way faster, but the overall performance wasn't. So even though with these performance improvements, we measured this, and Android was still almost 10 times slower than iOS in most tasks, running inside the SDK, so not affected by the Unify change. And after 3 years of suffering this, we wanted to make a change. So we went on an adventure to figure out why this was happening. The case of study here was loading the timeline because it was one of the most evident places where the performance was way worse on Android than on iOS. On iOS, most of the time this was instant, maybe 50, 100 milliseconds to load a room. On Android, this could take from half a second to 4 or 5 seconds. So it was terrible. So we started manually measuring the time spent doing each task when we load the timeline, and we found two main sources of slowness. One is read receipts, which are updated and computed every time we open a timeline, and loading the room members associated to the timeline events we receive. We tried first checking if computing the read receipts could be optimized, but it's a very, very complex code, and we couldn't find any quick wins, so we focused on improving the room members loading. So what does exactly loading a room member mean? It means loading lots of data, like the mroom member event from the state store, or the database. Its presence in memory database. Profile data from the state store, again the database. The disambiguated name, which means loading also other user IDs from the database. So you might have noticed a pattern here. And this had to be done for every single room member for every single timeline item we received when we open a timeline in the app. So we tried several things to improve performance. One was adding a cache to avoid loading the same room members again and again for items we received at the same time. An example, if you are in a DM room and you receive the first 40 timeline items, previously you'd load the room members 40 times, even if there maybe only one or two. So with this cache, we only did 2 of these operations. We also used the existing database collection pool to perform these operations in parallel as much as possible, because previously they were done sequentially. So it wasn't great. We had like 20 available threads and we were using one. So yeah, not great. We also found that getting this reconnection from the database pool could take from 1 to 4 milliseconds in a worst case scenario when the database was super overloaded. So we removed this check because basically checking the connection status in a remote database makes sense because your connection might drop. But checking it for a database that is on disk means that if something went wrong, probably something went very wrong in your device. And finally, we also tried, out of desperation, disabling encryption in the local databases and measuring again to check if this had any impact on performance. So did that help? Kinda, but not really. So we had performance improvements, but they were noticed on both platforms. So it means they were in the root of this issue. And the performance gap was still 10 times. And we hadn't actually fixed that. So although the DB connection could take that long, removing it didn't get Android anywhere near iOS. And removing the encryption layer that we have in the database made Android way faster, like 10 times faster. So we thought, finally, we're getting somewhere. But then we tried removing it on iOS, and it seems like the gap was still 10. So what now? We knew that Android's way slower than iOS, but performing tasks associated with the room member loading, which consisted of fetching data from the database, decrypting that data, and deserializing the JSON from that decrypted data. So if you have the same code for both platforms and nothing else changes, that means that the output of that code is probably different and it's treated differently in both platforms. So we went to the next step, which is Rust flags, which is basically a way to make sure you take advantage of the optimizations in your architecture of your device to make sure you use the most performant way to perform some operations. So what we did is check what Rust flags were enabled by default on iOS, and it seems like they were AAS, Neon, PMUV3, SHE2. So when we checked this on Android, only the Neon one were available. And disclaimer here, we had already tried modifying these Rust flags before, and it hadn't worked. But this time, we copied those from iOS, and suddenly something happened. We got an early Christmas miracle, and the app was incredibly faster, like a day and night. So what changed? It turns that the Rust flags are only applied to code that you recompile. So if you don't rebuild the whole project, it turns out we were applying the Rust flags only to the Rust crates and not to every dependency that we had in the project, like the dependencies we use to fetch data from the database and decrypt things. So we were applying some optimizations to code that didn't need any optimizations. So with this, we're done, right? Well, no, of course not. It can't be that simple. We received some reports from users saying that, yeah, the performance was way better than before, but there was still some slowness for some reason, and it seems to get worse the more you use the app. And it turns out fragmentation is a thing in SQLite. So if you add lots of records or remove them, and you don't kind of optimize the DB afterwards, you need to run the equivalent of the fragmentation, or otherwise the performance will drop significantly. So you need basically to use vacuum, which is a vacuum operation, and everything as soon as we tried that, everything went back to the optimal speed that we found before. So finally, it's done. We're not really 100% at iOS level, but we're not 10 times slower than iOS. So I call that a win. But we should as hell didn't want to go through that again and go through to that rabbit hole and try to figure out why performance is suddenly again slower. So we started adding some metrics to the applications. Basically, so we can detect trends or check what's the direction something is moving in some specific devices. If we know which one are, for example, our test devices. One example is this call start one. Like we can measure that from the app start until the room is fully displayed. It takes 1 and 200 milliseconds. What is that in detail? Turns out with Sentry you can add child spans to the transactions, so we can have a trace view with a lot more detail than before. And we can, an example, see here that just loading the UI for the room takes 40 milliseconds after the 87. And getting the first time items could be this small gap between the get and display first time items and the operation below, like 4 milliseconds, and everything else is mapping and displaying it on the client. So this gives us some hints when we find some new issues as to where this where the time is being spent. But we can still go deeper. We can have more detail because it seems like Sentry has a thing called distributed tracing, which allows us to stitch together transactions and spans from different systems. So if we start some operation in the client, like Element X Android, we can actually tell the SDK to also start a bridge transaction. And we can basically check what the whole trace could look. Let me see if this works fine. Okay, I assume you can see it, right?
Yep.
So this could be an Element X Android trace, open a room and see all the items in the timeline. So we load the room UI, we get the joint room, start the timeline. But if we somehow think the timeline is taking too long to load, we can click on this plus button. Yeah. And we can see every single operation done in the SDK during that time. And we can try to figure out what is that made it so slow. And that's actually not all we're doing in the matrix part of this. We're actually adding some metrics for other UX flows, like open notification, and we also want to start. We add one to check how long your first sync takes, and we also want to add some anonymized values, like hash home server value, or how large are your DBs or databases to know if this can somehow affect performance. And yeah, we can use that data basically to extrapolate what could be causing the performance to be great. And yeah, that's all. Thanks for watching. Any questions?
Jorge, that was tremendous. That is almost a conference talk in itself. And my only sadness is that we couldn't give you more time to take us through the storytelling there. Super stuff. Fascinating demo. Thank you for taking the time.
Thanks.
All right, Andrew, I don't know what this one is. Fun new Matrix Spec website features.
Yes, I will show them once I can share my screen. Good Lord, that was lucky. All right. Yeah, a couple things that just popped up today. I thought I'd show them off. The first one is a new feature added by Johannes to the spec website. There is now a drop down here. You can pick previous versions of the specification. So no longer do you need to edit the URL in order to get at an older version. That's pretty nice. The other thing, I just did some hacking today on this. I added a list of endpoints to the top of the
Hallelujah.
text. Yeah, just like the good old days. So yeah, website's getting better every day. That is all.
Cool.
Thanks, Andrew.
Thank you very much. All right, Matrix Live, that is your lot for today. See you next time.